this session, we will talk about X-bar and range control charts. The learning objectives for this session are to understand how X-bar and range or R charts are used to monitor and control quality. We also want to calculate the 3 sigma control limits for an X-bar and R chart and understand the most important considerations for designing X-bar and R charts. And this includes sample size, sample frequency, and the sigma level selection. And then finally, we're just going to briefly review the main steps in implementing statistical process control, or SPC. So in the last section, we mentioned X-bar and range charts, or R charts, in which we have samples of 4 or 5 observations each are taken at regular time intervals. And the sample average, X-bar, and the sample range, R, are computed for each sample from the sample observations. And we said in this lecture we want to answer the following questions. What is the center line? How do you calculate the upper and lower control limits? And for this we'll need 3 sigma. How will we do this? What is our estimate for sigma? So I have to bring you back a few lectures to answer these questions, because first we have to go back again to our normal distribution. So for a normally distributed random variable, here we call it X, we have a distribution function with 2 points of inflection which occur at a distance sigma from the distribution mean. And do you remember we were using an example of a table factory where our random variable was our tabletop length? So if I draw my table here, tables, and we were looking at the tabletop length, X is our random variable. Now, as we mentioned in the earlier lecture, if our length is normally distributed, then we would expect in this area here, between plus and minus 1 sigma of the mean, we would have about 68% probability that all of our tabletops will be between these 2 limits, between plus or minus 1 standard deviation of the mean. So now, we said as well that if we went out to 2 sigma from the mean, and we looked instead at this entire area, we would find out that about 95% of all our tabletops would be within plus or minus 2 sigma of the mean. And if we stretched our normal distribution out 1 more sigma, so that in total we were in plus 3 sigma and minus 3 sigma of the mean. If we colored in this entire distribution, it's quite easy to do using my pen here, we would find out that about 99.7% of all our tabletops would lie between plus or minus 3 sigma of the mean. This means that almost all of our random variable, almost all of our tabletop widths, even though they can never be perfectly similar, even though they can never all be exactly on the mean length, they will be within 3 standard deviations of the mean. Now, we also showed this slide the last time, but here's the first quiz. What's different in this lecture than last lecture? What have I changed? Let's see, maybe the title has changed. Because this slide we used to talk about the central limit theorem, and now I've changed the name to natural control limits. So we're measuring our tabletop lengths X. We have our tabletop lengths that are normally distributed with a mean and a variance. We take samples of size n, and we measure the sample average. And because of the central limit theorem, we know that this random variable is also normally distributed with a mean mu and a variance of sigma squared over n. We also know that if we don't even need x to be normally distributed, as long as n is big enough, we know that the sample average, x bar, will be normally distributed with mean mu and variance of sigma squared over n. We drew a picture of this here. This is the distribution of x, mean mu, sigma. And here we have the distribution of x bar with mean and mu, and standard deviation of x bar is equal to the standard deviation of x over the square root of n, which we show here. And that is smaller than our standard deviation of x. So now, what we had just said was, if the process distribution hasn't changed in any way, then we can expect that 99.7% of all of our x values, actually 99.73% of all of our x values, will fall within 3 standard deviations of the mean. And so what we have here also new in this slide are 2 limits. The mean plus or minus 3 times the standard deviation of x bar. And we can expect, if I scribble this in here as well as I just did before, that for all of our samples that we take, the sample average x bar, 99.73% of all of our x bar values will lie within these 2 limits. And these limits we call the natural control limits. So in this lecture, we're trying to bring many of the things we learned then together and apply them for quality management. Okay. Now, we also saw this slide. This is a typical control chart. So let's just go back to the 2 sources of variability. We had one source of variability that was chance causes, or common causes, and we had assignable causes. And the control charts are used to differentiate between them. The chance causes or common causes are these small unavoidable variability that arises from natural differences in the material, the manpower, machinery, instruments, and the environment. And these are to be expected. And normally they cannot be eliminated without a large cost. But from the assignable causes, this means that we could have a specific occurrence of a broken machine, some problem, some fault, operator fault, something that occurs unexpectedly and unwantedly. So the control limits, the upper limit and lower control limit of our control charts, then they should be able to monitor the chance causes, number 1 up here. So here again we have our picture. We have a center line, upper control limit, lower control limit, and each one of these x values is the average value of a particular sample, plotted, for example, against time. And if these values are constructed according to the 3 sigma rule, this means that we have 99.73% of our x bar values will fall within those 2 limits. And this should then cover 99.73% of our natural variability, our natural chance causes. However, when one of the points goes out of control, the assumption is that that's a very unusual situation if it were a chance cause, and this is most likely due then to some kind of assignable cause. And that's what the control chart is helping us to identify. So one more time, the control limits, if we use the 3 sigma rule, represent the limits for chance cause variability. And these are computed using data then drawn from the process, which is what we're going to do next. So Now let's just take one more look at this. Why are we using these 3 sigma limits? So it was Dr. Shewhart who recommended the use of the 3 sigma rule for calculating control limits when he originally proposed these control charts. And he did this because he wanted that the chance for a process interruption due to some kind of false alarm would be very small. And he chose the criterion that the chance for looking for an assignable cause when there was no problem should not be more than 3 in 1,000. So this translates then to the 3 sigma rule when the process distribution is normal. And according to this rule, the control limits will be placed at 3 standard deviations of the statistic being plotted from the center line. Now, you can change this if you want. If you want to place your limit at 2 sigma or 4 sigma from the center line, that's very possible. If your limits are closer together at the 2 sigma distance, then your control chart will detect changes in the process more quickly and will detect even smaller process changes more effectively compared to 3 sigma limits. But there will be also a higher probability of a false alarm. If the limits are placed further apart, say at 4 sigma, then we have a lower probability of a false alarm, but you may not be able to detect something with an assignable cause so easily. And even if you have a sizable change in your process, you may not detect that as quickly. So false alarms cost money because you may end up having your process stopped. So therefore, Dr. Shewhart argued that only assignable causes that can be found without costing more than it is worth to find should be discovered. And in his experience, it was the 3 sigma limits provided a good economic borderline. So again, talk about economic borderline. This depends on the cost structure of the process. If a situation exists where it doesn't matter if you have a false alarm, then you could locate the control limits closer to the center line. And then you can detect changes more quickly. If you have false alarms that are expensive, then you could locate your control limits further away and risk not detecting a change in the process, saving the expenses from a false alarm. So now let's look at this more practically. Let me draw this. Here we have a process, normally distributed process with time, and we would then construct our 3 sigma limit. So if this is the mean, it's hard to write sideways, this would be your upper control limit and your lower control limit there. And what we expect is that 99.73% of our values will fall between those 2 limits. So everything is fine, go along with time, and then suddenly there's a change in the process. Something happened and the process shifts. Now we would expect to see some percentage of the values moving out of control. And that then would be flagged. Or in this case, what we see is that the variation has increased here, and we would have a certain percentage of the values, the sample measurements, would move out of control. So this maybe gives you an idea of how these control limits would work. So now, we mentioned also in the last session that measurement control charts are designed to control measurements with the assumption that those measurements follow the normal distribution. And what we want to do is control the average and the variability of the measurement. And for a normal population, we can control the sample average. And for variability, we could look at the sample variance or the sample range. And these 2 values, the sample average and the measure of variability, those are statistically independent. So this means that if we control the sample average, we will not be controlling the process variability and vice versa. So we need 2 control charts. One that uses the sample average to control the process mean, and another that uses the sample measure of variability to control the standard deviation of the process. And the most popular combination then are your X-bar charts for the process mean, and the range, where the range is the sample maximum value minus the sample minimum value. And this, of course, is easy to understand. So whereas standard deviation is a little more difficult, sample standard deviation. So sample size, typically for X-bar and R charts, sample size of 4 or 5 is recommended. Now, why is this? Again, we go back to Dr. Shewhart. When he first proposed these charts, he recommended the use of as small a sample as possible, because if you're averaging over a large sample, you may hide an assignable cause that may occur in taking of the sample. But he also recognized that samples should be large enough to take advantage of the central limit theorem. And at the time, because there were not any electronic calculators available, the number 4 was advantageous because you can calculate the root mean square without doing any calculations. So that was an advantage, and that's why n equals 4 was commonly used. And later there was some advantage shown if there was a sample of size 5. So samples of 4 or 5 became very typical, the norm for X-bar and R charts. Now, the other decision that needs to be made is the frequency. How often should samples be taken? And here you need to have a balance between time, cost, and effectiveness to optimize your control operation. For example, if you have a destructive measurement, meaning that your sample is destroyed, it's better to take as few samples as possible while still keeping a satisfactory level of control. And one approach here would be to take samples more frequency during the initial stage of controlling a process, and then reduce the frequency once the stability is attained. So finally, as we said before, samples are taken from the process at regular intervals. The sample average X-bar and the sample range are computed from those samples, and these values are then compared to the lower and upper control limits to see if the process is in control or not. So how do we construct our 3 sigma control limits for the X-bar and R charts? To do this, first you need about 25 samples. It's recommended. And you need to calculate the average of all 25 sample averages. This is X bar bar, and the average over all sample ranges, which is R bar. And then using these values, the 3 sigma control limits can be computed as follows. So the upper control limit for the X-bar chart is equal to the X-bar bar value. So again, the average value for all 25 samples plus a constant A2 times R bar. We'll come back to that in a minute. The center line for your X-bar chart is just simply X bar bar, and the lower control limit is going to be X bar bar minus A2 R bar. For the range, the upper control limit for the range is going to be a constant D4 R bar. The center line for R is going to be just R bar. Again, the average of all the ranges for all 25 samples that you've taken. And the lower control limit of the range is equal to a constant D3R. Now, we've made this important point that these upper and lower control limits here, they need to reflect the 3 sigma limits, the natural control limits, where we know that within these control limits you have 99% probability that your values will fall between those limits. So the way we do this, these factors A2, D3, and D4, these can be obtained from standard tables, which I show on the next slide. These reflect the 3 sigma limits for the statistics X bar and R. Now, this is not included in this lecture, But if you're interested, you can look into our textbook in Chapter 5 for a detailed discussion on how these formulas are derived. But what we need to understand is that these factors will give us then the 3 sigma natural control limits that we're interested in, that Dr. Schuett recommended. So, and you can see them here. So in this table, there's various different factors. These are for different types of control charts. But what you can recognize here is the factor n, the number in our sample. And we did mention that practical sample size is 4 or 5 is recommended. And if you average over a large sample, you may hide the assignable cause. And if you need to have at least a sample size of 2 to be able to calculate the range. So here you have the A2, which is used for calculating the X-bar control limits, and your D3 and D4 used for calculating your range control limits. So I've talked a lot. There's a lot of numbers here. Let's do an example together. And our goal is to create an X-bar and R chart for controlling a process parameter. Example. We have the measurements for a net weight of chemical in a filled bag. So X are used to control the filling operation in a packing shop where a powder chemical is filled in bags. The average and variability of the net weight of all the filled bags should remain consistent, and X bar and R charts are used then to control this process. This is a real case from our author. He had 24 samples because 25 were not available, of 5 bags each. So n equals 5, were collected at approximately 1-hour intervals. And the X bar and R values were calculated for each sample. And the data set is included in the course if you would like to redo this example yourself. But here we see the data. So what we have on the top row here is the date and the time. So 10:30, 10:50, 11:45, different intervals in time. We have n equals 5, 1, 2, 3, 4, 5 sample measures. And you can see at 9:30 on September 21st, the following 5 measurements were taken with an average X bar 22.9 pounds and a range of 2 pounds. Again, this was the weight of a filled bag of chemical. So we have here sample number 1, sample number 2, sample number 3, sample number 4, all the way till sample number 24. Don't have 25 samples, but we have 24 samples. We see the raw data here for 5 measurements per sample over a period of time. Now, what do we do next? Our first step to create these control charts is that we need to calculate X bar and R bar from the first 25 or here 24 samples. So to do this, you need to take the average of all these X bar values and the average of all these range values. If we do this, we find out that X bar is equal to 21.37. In this case, it's pounds. And the range, the average range, is equal to 3.02 pounds.